In this video, we're going to go through two tables, one of common discrete distributions and the other of common continuous distributions. I expect that you have seen these distributions in your previous probability course, and so we're going to go through them just to refresh your memory on some of the aspects that are important about each of these distributions. So the first in the discrete table is the binomial distribution, and each of these distributions has a set of assumptions or conditions where it applies in a real-world situation. I expect you to know those and to be able to use those in word problems. Binomial distribution has two parameters, n and p. It's got a third q, which is really just 1 minus p. It's the complement, so it doesn't count as a separate parameter, but you do see it in the formulas here. The support as the values that a binomial random variable can take. Here's its mass function, the expected value, and the variance. The negative binomial has k and p as parameters. Its support is k to infinity, mass function, mean, and variance, given right there. The geometric is actually a special case of the negative binomial. It's the case where k is equal to 1, and if you plug that in, that's what you get. So it's not strictly speaking a separate distribution, but it arises naturally enough on its own that it is given its own name. So it has a single parameter p. Its support is from 1 to infinity with these mass function, mean, and variance. The Poisson doesn't fit any sort of natural process, but it is a very important distribution for modeling. It has a single parameter that we're going to call lambda, a support from 0 to infinity, a mass function here, and mean and variance that are both actually equal to lambda. The continuous distributions that I expect you to know are the uniform, the exponential, and the normal. So the uniform distribution has parameters a, b, and its support is the interval from a to b. Sometimes given as open, sometimes given as closed, but because it's continuous, it doesn't really matter. Its density function is a constant, 1 over b minus a, and that interval, and 0 otherwise. Here's its cumulative distribution function, expected value, and variance. The exponential and the Poisson are related, and so we use the same parameter lambda for them. The support for the exponential is 0 to infinity as an open interval. Here is the density and the cumulative distribution functions, the expected value and variance, and the normal, of course. The normal you will not be calculating by hand. You'll be using standard normal tables, but for reference, here is the density function. This refers to the standard normal table. So when we say phi, that is the standard normal table lookup. That's the normal table where you'll get those values. The mean of the normal, the normal has parameters mu and sigma, and those are named exactly because we have them. It turns out that the mean is mu and the variance is sigma squared. So those distributions I do expect you to be able to know and use in word problems, and to know the conditions that describe their use and what conditions relate the Poisson to the exponential variable. And we'll do problems on these as well as all of the information in the previous videos of this section to solidify this knowledge that we've gone through rather quickly, to brush up on concepts covered in your previous probability course.